Hello everyone, my name is Christopher and welcome to Machine Learning Made Simple. On this episode, we're going to be talking about the k-nearest neighbors algorithm. So yeah, let's jump right into it, or KNN for short. So let's take a look at a bit of a breakdown of this particular algorithm. It's a supervised algorithm. It's used for classification, and its subcategory is instance-based because it's, of course, it's based on instances, as we'll see in a second when we actually get into the algorithm itself and how that stuff works. So it can execute in O(d) of n time. O of dn time, where n is cardinality and d is dimensionality of vectors, which are, if you don't know what that means, that's okay. And finally, to get the most out of this video, it's preferred that you have a basic understanding of vectors and trigonometry. Nothing too complex, just mostly that you know what they are, how they work, and all that jazz. So after all that, let's go. So how does the algorithm work? And kind of what does it do? Well, we start by taking an instance of an unknown class. Remember, our instance are our columns. So these are objects with properties or features, as we refer to them. So we have an instance and we want to classify it, but we don't know what its class is. And class ends up being the target. So we need to determine the k nearest instances to this class. So, for example, if we have an instance here, right? This is and if we call this our target, we'll call this t. Or this is our input, so we'll call it I instead. And this is another instance, we'll call them A. It's another one, we'll call them B. And then over here in green, we'll say instance C and instance D. So this algorithm says is from I, which are the k nearest instances to this one. So we can see that B and k is of course just a variable, which we can use in our tweaking stage of the machine learning lifecycle. So B is the closest. So if k is 1, we're only looking for the single closest instance. And then if this is the case, then we can say that I is whatever target B has. In this case, it's red. If we say k is 2, the next closest one looks to be C. So your target for your instance could be, your unknown instance could be B, it could be red or green. And in this case, we just take we pick a random one, and we continue again. We say k is 3. Well, I think I is the next closest one. So then we can say the majority of the targets are red. So we say I is red. And if we even say this is 4 now, then it's an even distribution. There's the same number of red as there are green, so we just pick a random one and use that as the class to classify it, our unknown instance as. And yeah, got ahead of myself there. The class which makes up the most of the nearest instances is the target that we're going to go with. This should actually say target. That's my bad. So how do we do this? We do this by vectorizing our data, or turning our data into vectors, which is the really the tricky part of this algorithm. So how do we convert an instance into a vector? This is the million-dollar question. This is the reason that data scientists get paid so much. That's why they're so important, because anybody can just throw some numbers into an algorithm, some kind of library, machine learning. But the role of a data scientist is how do we put it in a format, the most efficient format to use. So how do we So yeah, it differs from situation to situation. That's the most important point here. There's no one answer to do this. It depends on the situation and all the features you have access to and the target that you want. So basically we just arrange every relevant, so the keyword here, relevant feature of the instance and place it into a vector. And the other key note here is same order. If this is alien to you, let's give an actual example here. Say we have this table here of people at a company. So as we learned in our first video, this right here, that is an instance, and this is a feature of an instance, this is a feature of the instance, this is a feature of the instance. All these are features, this, and this are all features. So what our goal is, we have to turn this data into vectors. So we essentially have to sit here and think, what affects what? We know positions are target, so we'll put a T there. So what features of these instances do we think can affect this? Well, probably the number of years, these are the number of years of experience that this individual has in these programming languages, and I'd say that probably affects them. There are ways of using text in this, but those are used in different algorithms. So nothing we're going to really touch on today. So we can't use name because it's text. And does age affect position? I mean, it sort of can, but I don't think so. Not in this case, just because it doesn't depend. It doesn't matter. You could have started coding later in your life or earlier in your life. Your age really doesn't matter in this case. So the ones that do matter, though, are the number of years of experience you have in each of these three programming languages, Python, Java, and C#. So if we create a vector and we say that the order of a vector is Python, Java, C#, like this, then we can generate a three-dimensional vector, or a vector with a dimensionality of 3. And we can tell it's a three-dimensional vector because the vector contains 3 items in it, 3 numbers in it. Now the thing about this algorithm is every vector has to be of the same dimensionality, for reasons which will become a little bit clearer later on in this video. So if we go ahead and start with this one for Adrian, then the vector we create is 565. For Lillian, 951. For Jose, 8610. And Fletcher, 113. And you can see we have these nice vectors, which become incredibly useful. Most of machine learning is actually based on vectors and matrices. K-nearest neighbors is really nice because it only uses vectors. We don't have to worry about using more advanced linear algebra, which is always a good time. So now we've vectorized this data and converted it into, one thing to mention, three-dimensional vectors are not the limit to the number of things in vectors. Generally, when it comes to real-world data science problems, you're realistically looking at vectors which are hundreds of dimensions. We can't even fathom something that's like a line that's 100-dimensional, because we live in a 4-dimensional world, because, of course, 3 spatial and 1 temporal dimension. But that's just generally, there's just usually that many instances, there are that many features which affect the target. So now now in this example, let's add one more, let's throw a curveball. There's a new hire. Somebody just got hired. Call him Egbert. He's 5 years of experience in Python, 5 years of experience in Java, and 10 years of experience in C#. So he has a vector of 5, 5, 10. So the question is, which position do we give him in this fictitious world where where the company assigns your position for you. You don't apply to a specific position. And also these numbers are completely made up, so the end result may not make total sense just because of the actual result itself may not make complete sense, but again, it's just for example's sake. But in the real world, things generally make sense. Your intuition is really your best friend when it comes to working in machine learning. So let's start with a small example instead. We'll come back to that data in a minute, but I want to use numbers that are a little easier to use, just because it'll make it easier for me to explain with smaller numbers and with only 2 dimensions. So the question is, and more classes, because in our previous example here, we only have every class, every unique target only has 1 instance there, which is good. We can use k-nearest neighbors search, which is the same principle here, except instead of what's the k-nearest neighbors, k is used for search results. So that's how a lot of search engines work. They use either k-nearest neighbors or another classification algorithm as search. But that's not what we're here really talking about. That's kind of a little extra fun fact there for you. So this one has more items per unique target. So we have 3 green and 3 purple. And the question is, where will this vector, where will this point fall? Now, we can actually graph these points to give us a better understanding of how this is going to work with this nice little graph here, courtesy of Desmos Online Graphing Calculator. So we can see we have our green points up here, our purple points here, and our blue one right here. This is our unknown. You can't see my mouse when I move it. Oh, yes, you can. Never mind. So this is the target we're looking for. So we have a good question mark. So just by looking at this graph, we can say that 5 and 6, yeah, this seems to be the closest 2 vectors to each other. So if k is 1, then we can say that green, the target, is green. However, when we say k is 2, then the next nearest one seems to be this 10, 4 here. Put another arrow there too. So this can be green or purple. And then when k is 3, the majority of these classes are purple, so it will definitively be purple. And the value you set k to is something that you have to set in the tweaking stage of the machine learning lifecycle. As I said, there are ways of calculating the optimal value here, which is to, again, use the 20-30 rule, or 70-30 rule, where you train with 70% of your data and you test with 30% of your data, of your known data, and then of the percentage that passes, you can kind of assess the algorithm. So the rule of thumb is you can usually calculate the percentage of that for every k value from 1 to 25 usually is a good number, and then whichever one yields the highest accuracy is the k you want to go with. But again, that all comes with tweaking and things like that. So the question is, how do we actually calculate the distance between a vector? Many of you might be sitting there thinking Pythagorean theorem, and that's not the only way. I'm getting ahead of myself. Yeah, how do we calculate the distance of the vectors between A, we'll call this, and A being the other vector, and B being our vector in question? And there's, of course, many ways to do it. You might be sitting there thinking, just use Pythagorean theorem. But there are other options other than Pythagorean theorem, 5 major ones, and they actually do have their own advantages, which are nice. So here are the five, I guess, most common ways to calculate the distance between two vectors. So we have Euclidean distance. If this looks like alien to you, when n is 2, or our dimensionality is 2. So for example, like we have a vector, like in this case, we have a dimensionality of 2 because each vector has 2 items in it. This ends up just being, c is the square root of a squared plus b squared. So, our squared Euclidean matrix distance is c squared is a squared plus b squared when our dimensionality, we have a dimensionality of 2. This right here is Pythagorean theorem. The nice thing about this one is this is the one I generally like to go with, the squared Euclidean distance, because you don't have to take the square root of each item. You get to leave all your numbers as integers, which I'm a really big fan of because, of course, floats and things like that require more memory and are more memory intensive. So just omitting the square root when we're using a small example of like 6 or 100 or 200, it's not going to make any difference really at all. But again, in the real world, with machine learning, generally you're working with millions, sometimes even billions of records. So every optimization you can possibly make will make a world of difference when it comes to training your algorithm. We can also use Manhattan distance, which is always nice. Oh, by the way, which would be would just be a plus b. We have a minus b here, and what that's doing is it's just taking. So we have the two vectors, 1 and 2, and we'll say 4 and 2, and then we'll say 1 and 1. It's just saying 4 minus 1 and 2 minus 1. So you have 4 coming from here, our 2 coming from here, and our 1 here, and our 1 here. And this is going to give us 3, 1, 3, 1. So if we were to use Euclidean distance on this, we would have c is equal to 3 squared plus 1 squared, the square root of this. And then, of course, Euclidean squared would be c squared is equal to 3 squared plus 1 squared. Maximum distance is just, I don't really like maximum distance just because it doesn't involve all of the data in all of the numbers. It just involves the furthest one. So in this case, 3 is the biggest value in this vector, so the distance is 3. And of course, each of these will return their own different results, but they'll be about the same when you proportionally. And the last one is, I can never pronounce this one correctly. I always butcher the name, but I don't like using this one because it involves like a covariance matrix, and actually involves using matrices which get computationally expensive. And again, using like inverse, it's using the radical signs. It's transposing the matrices, which does again make things very computationally expensive. So I'd like to try and avoid that. So if we go with the squared Euclidean distance for each of these points, we can easily calculate the distance between them as 29, 5, 13, 10, 25, and 8. So again, if we were to order these, you would see that. So if we were to analyze, do a k analysis, I guess, when k is equal to 1, what is the smallest item here? Well, it's 5. 5 is green. So if k is 1, then this becomes an instance of the green class. The target becomes green. If k is 2, however, we can see that our two lowest numbers are 5 and 8. 5 is green, but 8 is purple. So we'll have to pick random green or purple. When we go to, if we set k to 3, however, we can see that 5 is the lowest, 3 is the second lowest, and the next lowest to that is after that is 10. And 10 is purple, so we have 2 purples and 1 green, so our target becomes purple. And of course, you just continue this as much as you wanted k to be. I usually like to keep it at 3, but in examples like this, of course, when you get into, again, millions of records, then you need to adjust according to your data. So let's go ahead. I'll give you a chance to try it yourself based on our data from before. I want you to determine which job Egbert will get if k is 1, 2, and 3. So just pause the video real quick and let me know your thoughts. And figure out for yourself, and we'll see if you how well you guys do. And of course, in my example, I'll be using Euclidean squared formula. Squared Euclidean distance, which is this one, or just this one. So in this case, it would be 5 squared plus 6 squared plus 5 squared for this example. Yeah, but sorry, spoiler alert, I guess I should have said. So yeah, pause the video and go ahead. Okay, so if you figured it out or decided that you don't want to figure it out, which is more than okay, let's take a look. So I've graphed these in 3-dimensional space. This graph is courtesy of course, GeoGebra online graphing calculator. We can see all of our instances in 3-dimensional space. 3-dimensional graphs are very hard to show on a flat screen such as this. But I did my best. Just as a little bit visual, but the most important thing is, of course, we can see the distance between Egbert and the 4 people who currently work at this company. And based on the distances, we can quickly order them and see that if k is 1, he's most similar to a junior developer because he's most similar to, oh, I messed up the names. The names are not in the correct order. That's my bad. Yeah, I messed up the names. That's my bad. I messed up the names here too. Okay. Sorry about that. Based on our first table. Can't believe I didn't notice that. Junior developer, Fletcher is a junior developer. He's most similar to Fletcher. So we can assign him the role of junior developer. And if K2, the senior developer, or junior developer, we can pick a random one. And then if K is 3, we have a junior developer, senior developer, or a backend developer. And that's how we can kind of classify him into a job based on his experience. All right. So again, thank you for watching. If you have any questions about this particular algorithm or any other algorithms, please feel free to leave them in the comment section. If you have any more algorithms or things you want to learn about, any subclasses like algorithms too, my next video is going to be on linear regression. I'm at some point going to post a video on writing a k-nearest neighbors algorithm in native Python, or as native as we can possibly get, just so we can really understand the algorithm, how it works, all under the hood. And then we'll be having some fun actually using real data, just small data sets, and with just some libraries. But the purpose of writing our own function in our own library for handling each algorithm so that we can really understand how it works at its core. And not only that, but mess around and tweak things just to see how it affects and really learn and kind of satisfy our curiosity. So yeah, thank you for watching. You are always more than welcome to like and subscribe. It's up to you, but it's much appreciated. Thanks for watching and have a nice day.